Right, this is a sort of bit of a synoptic question, I guess. We got matrix sort of determinants and inverse here, and then we've got a proof by induction for matrices uh, in this part two. Um, this proof by induction for matrices is a sort of a bit of a happy hunting ground for examiners. It's something they kind of seem to like to put together. So it's kind of worth just noting this. It's not a terribly complicated one, but anyway. Right, so this is from edXL, the specimen paper for Core Pure 2. So let's have a look. It's sort of manipulation of matrices, really. So here's our matrix. We've got a constant A in there. Now, they like these questions because, your calculators can't really cope with you putting unknowns in or sort of run-of-the-mill calculators can't anyway. So the question, sorry, that's question part one. And then subpart A, for which values of A does the matrix M have an inverse? Well, of course, that's tied in with whether or not the determinant is zero or not. If it's we've got a determinant of zero, then it will not have an inverse. So let's find the determinant. Now, what I've done here is I've used SAR's rule, which I think is I'm sure it's the easiest way to do the determinant for a 3 by 3 matrix. And if you haven't seen this, there, we write out the matrix there. And then if we write out the next whole thing, if we like, but we only need these next two columns here. And then what we do is we multiply those three, add those three, the products, and then add the products of those three. That's what we got there. And then we subtract the products of those three, and the products of those three, and the products of those three, and that's what we've got there. And that works out to 10 plus 2a. So that is the determinant of M. So if 10 plus 2a equals 0, then there is no inverse. There's no inverse. Just correct that. Does not exist an inverse. So in other words, when a is equal to -5. Right, so that is part A. So if you haven't seen Sarus rule, I should say, then I think that's quite neat. All right, part B. Given that M is non-singular, find the inverse in terms of A. Right. There's a couple of ways of doing doing the inverse, but I think this way using cofactors is probably the way to do it. Oh, essentially what it is that for this top left element here, if we ignore the first row and the first column and work out the determinant of what's left, okay, so it's that there. So the determinant is that. Then for this element here, yeah, we're going to take out that row and that column and that row, and you take the determinant of what's left, but apply a negative to it. All right, so it looks like determinant of -2, but in this cofactors, then we change the sign. And in actual fact, we are changing the sign of alternate elements. So we're going to apply the same treatment here to all these. So for this element here, we're going to identify that. We're going to take out those, and then it's the determinant of what's left. Again, subject to the sign, all right? And the signs basically go positive, negative, positive, negative, positive, negative, positive, negative, positive. All right, so those are the signs that we then apply once we worked out the determinant. Right, so this is therefore the matrix of cofactors of M. And then we want the transpose. So we just turn our rows into columns and vice versa, and that's going to give us that. And then the final step is we divide by the determinant. So the determinant we've already worked out there. And so this is the uh, the the inverse. And clearly, as you can see from here, if A is -5, then that isn't going to work because that's not going to be undefined. Right, so that is that. So just roll down to this proof by induction. Prove by induction that for all positive integers n, then this statement is true. Right, so okay, so our first step is to establish whether this is true for n equals 1, and I think we can see by inspection that that is equal to that. Yeah, so that's this matrix with 1 substituted in. So this is indeed 6. 3 minus 1 is obviously 2. 3 times 2. So it is true for n equals 1. We then assume that it is true for n, and so therefore the n plus 1th term, which is that, is actually equal to the nth term multiplied by this matrix, this multiplier. We're just increasing the exponent, if you like, by multiplying by that. And when we multiply that out, we get this. This term doesn't readily look like this, but it is just with a bit of manipulation. And if you need any convincing, then I've got a little panel in there that just works it through in a little bit more detail. All right. And so we can see this is exactly the form of our of here, except we've got n plus 1 instead of n. So that proves it. I mean, we could use m's instead of n's, and we kind of wanted to follow a bit more of a textbook, the sort of thing that textbooks do. Personally, think is kind of unnecessary. Once you've shown this is in exactly the same form as that, then that's proof done, as far as I can see. So there we go. So the fact that it's true for n implies that it's true for n plus 1, and therefore, being as though it's true for n equals 1, then it's true for all positive integers, because obviously what we've just done here proves that it's true for 2, 3, 4, 5, and so on. So that is the proof by induction. And hopefully that has been useful. So thanks for watching.